Today I'm going to show you how we can make some intermodulation measurements on active devices like power amplifiers, and we're going to use the 4-port ZVA network analyzer, which has the ability of supplying two sources with two internal RF sources inside the box. We have to consider first of all how we're going to make the two-tone combination of the signals, and we can do that in a number of ways. We can use these external B9 links that allow us to utilize the test port on port 3 of the network analyzer to combine the lower and upper tones into the DUT. We could use external devices like this power splitter to provide the two-tone stimulus, or if you have a ZVAX unit, then this conveniently takes the two signals and combines them nice and conveniently inside one box. For this setup, what we're going to do is use a directional coupler to provide the two-tone stimulus. I've chosen a coupler because this allows us to have low insertion loss in one RF path so that we can still measure the S parameters on port 1 as well as providing the two-tone stimulus coming in from port 3. So I'm going to go through the steps to calibrate this, and then we'll connect the DUT and see the measurements. First of all, what we have to do is set up on the network analyzer the frequencies of interest for the measurement, and here we're going to start at 1 GHz and stop at 2.4 GHz. We have to choose the number of measurement points, so here I'm going to choose 101 points purely for convenience of a fast calibration time with the power sensor. If we then go into the mode menu, this holds the applications which are optional add-ons, if you like, to the ZVA, and then here we can find the intermodulation distortion measurement function that allows us to utilize the wizard to set up the IMD measurement. In the dialog here, you can see that you first of all configure the two sources, so the lower tone, for instance, can come from port 1, the upper tone from port 3, and here we're measuring the output of the device at port 2 using the B2 receiver. We can select the measurement bandwidth of the receiver, so in this case say 1 kHz, and importantly the tone distance. We'll stick with a standard 1 MHz tone distance between the upper and lower tone. We can also define this for a mixer measurement if we're measuring IMD on a frequency converting device, and if we come down to frequencies and powers, we can then see we've got the start-stop frequency, and we can choose the CW power for the two tones. Choose OK. Further down, we've got preparation for the intermodulation order that we want to look at. If it's the 3rd order, 5th order, 7th order, then we click it here because this allows the analyzer to prepare itself for the frequencies that it needs to calibrate. And we also have the capability to have vector corrected wave quantities. By selecting this box, we then also have to perform an S parameter calibration. Choose OK, and now we will go through the calibration using the power sensor. So we connect the power sensor to the end of the directional coupler, and then in this convenient dialog all the measurements are configured. So if I for instance come in here, modify settings, we can choose the number of readings. We'll put that to say 10. The final tolerance of the value that we stop at, 0.2, convergence factor maybe 0.8, and then here we can see we're doing both a flatness cal and a reference receiver calibration. Now in this dialog at the top, if I click port 1, this is going to run through 3 different measurements here, or 3 different calibrations. The first thing it's doing, you can see here, it's calibrating the lower tone coming out of port 1 at -10 dBm. Once it's done that, it will then move on to also measure the frequencies for the 3rd order intermodulation products at the lower and upper sides of the carrier. This way we can then move on later and use the port 1 to also calibrate the receiver at port 2. So we can see that the lower tone here has passed, so we have a deviation of no more than 0.0 dB, and now it's moving on to look at the 3rd order intermodulation product at the lower end. So that's also measuring at -10. That's now completed. Now we also have to look at the third order product at the upper region. And there we have the first pass, and the second pass just gives a verification at the -10. So with that completed, then the next step, with the power sensor still connected to the output of the combiner, or the directional coupler in this case, we click port 3, and now the upper tone coming from port 3 is characterized. Now you'll see in this case here the initial signal is -30 dB. That's because in this case the directional coupler that we've chosen has a 20 dB coupling factor. So we have to make sure that the final value of power that we want for the two tones is able to be reached by the sources within the ZVA. Okay, and that's the source power calibration completed. So now we can disconnect the power sensor, and the next step you can see on the dialog is to connect the external device, i.e. the directional coupler, to port 2. And this is much quicker now because we're not waiting for the power sensor to go through sampling the data. So we run through lower tone, upper tone, then the intermodulation frequencies. Then once that's complete, we can see at the bottom, then the close button comes alive. So we can now click this, and now we have a fully calibrated system. So what we can do to start with here is, once we're calibrated, there's a button here called CW mode intermod spectrum. If you're more comfortable with looking at the CW products as a spectrum measurement, then we can click on this, choose the frequency, number of orders, say 5, click OK. And then we can see the value of the tones and the third order products here coming from the network analyzer itself. So at this point I don't have a DUT connected, I'm just looking at the capability of the ZVA receivers. If we just undo that, we'll go back to our swept measurement, and now in the measurement menu we can add the intermodulation measurement parameters. So to start with, we'll look at the lower tone at the DUT in, and then we can add another trace, and we can look at the lower tone, upper tone, sorry, at DUT in. So here you can see we've chosen to have power levels at -10, and we're sweeping from 1 GHz to 24 GHz, and the value that we see on the screen is -10 dBm. So now let's put the DUT in. Turn the DUT power on, and now what we can do is look at adding some traces, and what I'll do is just change that to a different diagram area, and down here we can look at third order product at DUT out, add trace, that's the lower, and then third order product at the upper DUT out, and then maybe we can also add the intercept point measurement. So at this stage here we're feeding tones in at -10 dBm, which is probably a little bit high to drive this amplifier, because we're getting close towards its saturation. So let's bring the tones down to -30, say. Now you can see that the third order products are coming down towards the noise floor. But if we look at the value of the two-tone signals that we're putting into the device under test, they're now 29.8, 29.5. So they're not really exactly on the minus 30 dBm that we would like. We power calibrated around 0, or in this case minus 10 dBm, because that gives us the best linearity for the power calibration, the best accuracy with the power sensor. But when we want to measure down at minus 30, we drop the signal down, and now what we can do is turn on the ALC, and here, if we go into the power bandwidth average menu, we will find the ALC config, where we can enable this for port 1 and for port 3, because that's the lower tone and the upper tone. For convenience, we can also select last measurement, because that then speeds up the actual measurement time, and maybe put a final value of 0.25 dB in here. And now you'll find here, if you look at the values of the markers, 29.9, 29.9. So they're now spot on, and we can change the power to whatever we want, minus 20, and we have a closed loop power control that then means we are absolutely confident with the power signals that we're putting into this device under test. When we're actually looking here at the third order products, extend the screen there, we can see the third order products down here. We can then see intercept point. If we want to reference the intercept point at the input or the output, then we simply come back into the measure menu and we go to more intercept point, and here you can choose the product, the side, whether it's lower, upper or major, and whether it's referenced to the input or the output. Now, I did say that the convenience of using a coupler is that we can also do S parameter measurements. So just to finalize the measurement here, we can then say add trace and diagram area, and then down the bottom we can measure S21, add another trace and measure S11. So we conveniently have our standard S parameters of our amplifier across the frequency range, plus our swept IMD measurements.